Flight testing of modern radar and EW systems, while exciting, especially for the pilot, is extremely costly and time-consuming. This has become a limiting factor in this era of budget cutting, with each hour of flight testing costing upwards of $100,000. Note also that test conditions such as temperature, sun angle, and pilot fatigue can make these results unrepeatable. What if, instead, we could virtually model the aircraft flight dynamics, 3D cross-section, and signal propagation effects, while at the same time modeling the radar system's performance to provide a complete operational performance profile under a wide variety of tactical situations? These runs could then be repeatedly performed any number of times while studying, for example, jamming effects or detection avoidance. Seen here is a virtual simulation of an F-16 using the STK software from Agi running with Agilent SystemVue software. STK models the aircraft flight dynamics, propagation effects including terrain and 3D radar cross-section, while SystemVue models the radar signal generation, the RF propagation using the data from STK, and the radar receiver including both RF and DSP pulse Doppler processing, with results being measurements such as probability of detection, spectral splatter, or time side lobe power. By integrating the capabilities of best-in-class software tools such as Agilent SystemVue with various software tools such as STK, MATLAB, and ADS, along with test equipment, design teams with very different tasks can work together to validate the complete design at every stage of a system's development process. Here is an example of a P-3 tracking two tanks as they cross the desert floor below. The RF transmitter and receiver are represented by behavioral models. They could be replaced by more accurate RF spectral domain models or even circuit designs based on co-simulation with Agilent's ADS. SystemVue allows implementation of DSP components as behavioral models, MATLAB algorithms, or VHDL models. Here the radar transmitter and receiver share a common local oscillator and therefore correlated phase noise at a 10 kHz offset. As the phase noise is increased in a swept simulation, the system's probability of detection, POD, starts to degrade suddenly, starting at -106 dBc per Hertz, with a 50% POD threshold occurring at about -101 dBc per Hertz. Therefore, poor phase noise can limit the system sensitivity and range, which is an important consideration for radar architects. SystemVue can also be used to evaluate other scenarios such as jamming or Keysight interference. The ability to simulate meaningful real-world radar scenarios helps to define system requirements much earlier in the development process. For additional information about SystemVue, please visit www.agilent.com/find/ESOF-SystemVue-info. For more information on this specific integration with SystemVue, or to learn about Agilent's ability to integrate third-party solutions for your application, please contact your local Agilent ESOF sales representative.